Hello, my name is Allen Hoffman. I'm a professor of mechanical engineering at Worcester Polytechnic Institute in Worcester, Massachusetts. This short video will provide you with a brief introduction to rapid prototyping. Rapid prototyping also goes by the name of 3D printing and also additive manufacturing. Now, in the normal manufacturing process using metals, that's subtractive manufacturing. In a sense, you start with a block of material and you take material away using some sort of machining process, be it drilling or milling or turning or other mechanical processes. In 3D printing, you start with a blank plane and you add material to it in order to create your part. Now, the process itself is very basic in the sense that if I took my glue here, now as just a very crude example of how 3D printing works or additive manufacturing works, we can consider if I had a glue gun with a material that hardened very quickly after I placed it on the paper, and I could place very fine lines of glue on the paper, I could gradually track over the paper and build up a particular shape. Now, if I had two kinds of glue, one which hardens and builds up the shape, and another which I can later dissolve out of the part that is created, I can create parts that are not possible to create by normal manufacturing processes. For example, this particular part shows it was just made as a demonstration, but it is a ball within a solid cage. Now, this is just an example, but if we thought of this as a very small part which had to be created with very reasonably high precision, that means I could create essentially a float valve in this manner. And of course, I'd have to have a fluid input on this side and a fluid exit port on this side, but I could create this part which cannot be created by mechanical means. What happens here is I create a solid part, and then in using two types of materials, and then the material that was originally supporting the ball is dissolved away. Similarly, we have a wrench here, and this actually works. And this was produced again using two materials, a base material, which is what you see here, and then a filler material, which was then dissolved away after the whole part was made. Now, next I'll go into what we a little bit of background here. Next I'll go into a little bit of background here into how the process works. What are the steps in the process of producing a part by additive manufacturing? First of all, you need some sort of CAD model, a computer-aided design model of your part, of the physical model. And essentially this is a virtual model, exists only as a digital file. Usual programs that are used are Inventor or SolidWorks, or other programs can be used. The software involved in rapid prototyping then converts your CAD model to a stereolithography file, or so-called STL file, which really is the file that is fed, the digital file that's fed to the rapid prototyping machine. The rapid prototyping machine essentially creates a geometric model, a virtual geometric model that would look similar to a finite element grid, only it's 3D, or like a 3D finite element grid, and then that file is used to control the rapid prototyping machine in depositing these very fine layers of material that can be of different strengths, different densities, and as I mentioned before, some of them can be dissolvable after the solid piece is produced. Now, what we do here at WPI, we only involve essentially thermoplastics, plastics that can be melted and then harden up. But the field is moving very rapidly towards using other materials with greater strengths and greater versatility, and materials that are solid engineering materials will eventually be used in 3D printing. That's still a ways away in a practical sense, but there are experimental machines that do this now. Now, sticking strictly with thermoplastics, these materials, of course, have a certain set of material properties, and therefore that limits the use of what you produce. In other words, they are essentially a material that, when heated, gets to have fluid properties, and when it's hardened, you get something like this. One of the disadvantages is if I heat this part, I will go back to a more plastic state and lose all the dimensional tolerancing I have. Essentially, in considering whether to do rapid prototyping, we should consider the accuracy with which we can do it. The resolution is the smallest thickness that we can actually deposit in making the part. So essentially, it's the diameter of the nozzle on the glue gun. That minimum diameter is about 7 to 10 thousandths of an inch. So we can't get dimensional accuracy below that level, because that's below the level of a single strand of fluid material or semi-fluid material that's deposited by the nozzle. The other thing we should consider is the tolerance. How close can we make? How close are the tolerances, or how low are the tolerances in the devices that we can produce? And here again, that range is from about 2/10 thousandths of an inch. That would be a very highly accurate or a very low tolerance, up to about, again, 10 thousandths of an inch. The materials, if we talk about the thermoplastics, they have good ductility, they are low weight, so that should be considered in their applications. But again, as previously mentioned, they can't be exposed to high temperatures, or they will lose their dimensional accuracy, and at a certain high temperature they become fluid. We have here a few examples of parts. And there are parts that rapid prototyping is a good application. Then there are things that certainly some of my students try to do with rapid prototyping that is a very poor application of the technology. The major applications of 3D printing come from its origins. 3D printing really came into its own in about the 1980s, so it's not a very old technology, but it was brought in to having value in the engineering design process, first as a visual representation of your design. It is a quick way to get an accurate three-dimensional visualization of your design, particularly with respect to small parts. And so in prototype construction, maybe something like this, you can get a full-scale model and begin to appreciate all the geometry. You can use this wrench to turn a nut or a bolt. Again, there are strength limitations on the materials in this prototype, but you can get a good three-dimensional visualization of your design by 3D printing. It can be used for low-run commercial parts. That is, instead in using metals, subtractive manufacturing, we have to set everything up, and if we're only going to make half a dozen parts, that can make that small manufacturing run very expensive, whereas we can churn out 6 of these for the same cost, with no upfront cost once we've got the STL file. The other advantages are customized parts. We could make gears. Now this is a standard gear cut out of plexiglass, so this would not be a good application for rapid prototyping. But if we had a very unique set of gears that we maybe couldn't purchase at a reasonable price that we needed in a prototype, 3D printing might be a good application. We can get full-scale models. Here again is a model. In a little car, it's got gears here which turn. Okay, all the wheels turn. The rear axle has got a little mechanism in it. Probably hard to see in the video, but you can see that this is a very valid process. You can see the pistons here. I guess that's what they're meant to be. The pistons going up and down in a kind of a unique engine arrangement. That is 3D printed as a single part. To make this by subtractive manufacturing would take a lot of effort, and yet we can look at it, we can play with it, and so forth. There are so custom parts, small runs, discontinued parts. This has applications and mechanisms that might be antiques, where you can't buy the part, and you only need one, or two, or three. And that's also a good example. And then actually in personalized parts where you want to create custom jewelry or toys or things like this, we have here a little name tag. This is hard to get off the table, but on it has a little. It goes on a key ring. Got a little hole here. It's got WPI embossed on it. So if we wanted to try out different designs for this little part, we could produce all kinds of designs very quickly by rapid prototyping. We probably would not want to do a mass production run by rapid prototyping because it would be much more expensive than setting up the jig to produce 1,000 of these. There are definite misuses of rapid prototyping. Being in a university, I tend to see many of them. Students like the technology. It's an easy technology to apply, and therefore sometimes they apply it in a way that really doesn't make any sense. If we look at what is a standard screw here, that part can be bought. It can be made of metal, so it's stronger. So the idea of just producing this, unless this were a very custom thread that would be difficult to obtain, this is probably not a good use of rapid prototyping. Someone at our university tried to make an airfoil out of this. Well, again, this is a thermal process, and consequently, in curing, you've got to consider heat transfer, the heat transfer from the part, and this being a very thin part, as it cooled, it warped. So this wasn't designed to look like this, and the manufacturing process demonstrated that it was not a good application of rapid prototyping. So generally we wouldn't want to do it for available parts. Save your trip to Home Depot. It'll be more costly, it'll be weaker. It's just not a good application. Assemblies, I mean, in general, the assemblies are rigid, but I have here, again, I showed you two pieces that they are assemblies and they do move, and as well as this one also. That's a third one. To produce a solid assembly, in most applications you would produce a solid assembly, and so hence it's not useful. But we can, in complex mechanisms, actually make them on 3D printer. The other thing you have to be cognizant of, again, is of the thermal properties. That is, if you make a part, now you're going to cut and drill it. Cutting and drilling involves heat transfer, heats up the materials, and therefore changes the dimensions of your part. I have one more example that I haven't shown here. Here's an example of a good application of 3D printing. This was a prototype of a key holder for, say, an elderly person who has poor pinch strength, which is the normal way we hold the key. So we wanted to find out, can we design something that will give a mechanical advantage and make the grip different than this key grip that most of us would use to turn a key in a lock. So this is composed of two parts. The nail here is just in lieu of a pin that would be inserted into this. The nail is there so I can take the two parts apart. But here we have a mechanism that holds the key. It's got a cutout in it for the key. It can be made so it fits in your pocket or in your pocketbook. And when we want to use the key, we bring it up, okay, we bring it over, and now we can slide it into a slot in the mechanism, and now we have a key holder which uses a different grip, a cylindrical grip, which is generally our strongest grip in our hand. Again, the nail here just allows me to show you the three pieces. This piece, little half circular piece, again, might be hard to produce otherwise, and has a drilled hole in one end. Again, I don't think that would be visible in the video. So, in conclusion here, rapid prototyping has become a common and widespread technology to produce prototypes and to produce actual manufactured parts, and it will continue to become more important in the future. It's necessary that the people who employ it understand the limits of the technology at the present time and the application of the technology, so that we're not producing parts like this that we could run up the street to Home Depot and buy, and they would be better parts. Thank you very much.